So in this video we are going to learn time domain analysis using MATLAB. So in control system there are two type of analysis. One is time domain, second is frequency domain. So using time domain we can get like system how it is fast, what is the steady state error, is any overshoot, is any undershoot, what is the settling time, it extra we can know. From frequency analysis, we can find out that the system is stable or unstable and how much it is stable. From time domain, you can find out the stability, but you can't tell about like how much it is stable or unstable. You cannot find out the relative stability using time domain analysis. Today we are going to focus only on time domain analysis using MATLAB. Let us start. So what we are going to do, first order system specification, then second order specification. So let us start with first order system specification. So I have taken first order transfer function of 1 upon 2s plus 1, and this is where we can define in the MATLAB coefficient of numerator and denominator and transfer function. So transfer function is defined it, and I'm plotting the step response. So I can use the step function, and this is y output and the t step, and I'm plotting the graph of the step response. After that, I'm just checking the step response specification which I'm going to display, and I'm going to display the ramp input, and also we can say that what would be the steady state error for the ramp input. So let us start the code and let me run the code. So this is sections. I have written in section wise. So this is sections. So let us run this code section wise and let's see the output. So this is a transfer function 1 upon 2s plus 1. This is a step response and this is a ramping response. So let us understand. So in the case of, see, we are applying unit step. By default it is unit step input. So for that the final output is also 1, and the input is also 1. So 1 minus 1 0. So steady state error for first order system for a step signal it is a 0. Let me repeat, for a first order system step response that time steady state error is 0, which you can see from here. 1 minus 1 0, so no steady state error for step input. For ramp input, if you see, this is a input, the red color dotted line, and the second one it is a output. So if you see, the difference between input and output is 2, right? So in case of ramp input, there is a steady state error. And what is steady state error? If you observe, this is a 2, and if you have seen the time constant, it is also 2. So for ramp input, the steady state error is tau. Let us check once. Let me put it 3. So I'm here changing 3s plus 1, and this is just for understanding. This is comment. So I'm changing here only. This is not required, but I'm doing that just for understanding. So let us run the code, run the section. So now it is 1 upon 3s plus 1. And steady state error for step input 0 for first order system, and for here if you see the difference it is a 3. So how do we know? So we have calculated here. I will show you, I will tell you the what is it and all the stuff. So it is 3. So steady state error for RAM input for first order system it is a tau. Clear? Let me explain like for RAM input input is T, right? Miss what T is like we know that step it is 1, for ramp it is T, and for parabolic it is T square by 2. So there is no ramp function. There is a lsim function which takes any system. You can have any input. You have to provide a time, so you can find out the output, right? So you can see more the details. You can do this doc lsim to understand more on this. Any function, if you want to understand more detail, you can write in the command window doc, that is documentation of lsim function, right? So any other thing that I have to explain? This who everyone know, this is time from 0 to 30 with a step of 0.01. That is the meaning. So time is equal to 0, 0.01, 0.02, 0.03, like that till 30. So that is about the first order system. and we have seen the step response and a ramping response. So now let us see the second order time domain specifications. So for second order system, this is a for step response, this is a output equation. C of t is equal to 1 minus e raised to minus zeta omega nt upon under root 1 minus zeta square sine omega dt plus phi. Where zeta is called damping ratio, omega is called natural frequency, omega d is called damped frequency, phi is phase shift, right? So let us plot t versus c. So what we can do, we are putting t from 0 to 10 with a step of 0.1. Zeta I have taken from 0 to 1 with slider. How to enter slider? If you don't know, I'm repeating again. Zeta is equal to, you can write, you can go to insert, control, and go to slider. You can specify minimum 0, maximum 1 with a step of say 0.1 or 0.2, and default value say I want 0.2 or 0. Anything between 0 to 1 you can take. So you can have this kind of slider in the MATLAB live script. So I've taken zeta 0.4 and omega n 4. Now what is formula of omega d? It's omega n into square root of 1 minus zeta square. Phi is 10 cos inverse zeta, and this is C of t formula. Not that whenever you are doing vector to vector multiplication, you need a dot before the star, right? So that is the basics of MATLAB. Now plotted t versus c. So let us run the code and let us understand this. So let me run the section. I'm not doing this, I'm just running the section. So you can say that this is a first order system with zeta is equal to 0.4. Now let me make it 0 and let's see what is it. Wow, this is kind of pure sine wave. So when zeta is equal to 0, it is called undamped system, right? There is no damping, it is called undamped system. And you can see that when zeta is equal to 0, the complete cycle it is taking from here to from if you see here it is a 4 second, right? It is like 2 second, and if you can find out, you can find out the omega n as well. Now let us see the different specific. So when zeta is equal to 0, it is called undamped system. When zeta between 0 to 1, it is called underdamped system, right? Let me show you with 0.4, and if I take 0.2, there will be more overshoot, right? When you go from the zeta between 1, it is called underdamped system. There is no overshoot, right? Let me take 1.1. This is called sorry, 1 is called critical damping. More than 1, it is called overshoot. It is called overdamped system, right? So there are 4. Zeta is equal to 0 called undamped system. There is no damping, so undamped. Between 0 to 1, it is called underdamped system. When zeta is greater than 1, it is called overdamped, and zeta is equal to 1, it is called critical damping. And you can see the response and you can plot. Fantastic. Now let us see the specifications. Before we move to specifications, let us understand this is a link. You can insert link in between, and let's see what is it. Okay, so you can have a this I will explain later, but this is what second order specification. This is called peak, this is called peak time, this is called final value, this is called settling time, this is called rise time. So rise time, there are a lot of definition. I'm not going. The time required to reach 10 to 90% or 0 to 100% depending on the type of response. For underdamped system, it is between 0 to 100%. That is called rise time. The time required to reach to the maximum or final value. First thing, peak. Like this is, we can find out overshoot based on the peak, and there are different specifications. You can go to details. But here I have written the formula of different time domain specifications, and I have just I've just printed them. So let us run this, and here I'm getting different answer, right? Oh, okay, I have taken the different system, so let me check it. I have taken overshoot. I have to take it is for underdam system, so I'm taking any value between 0 to 1, and then let me run this again, right? So this is a delay time, rest time, peak time, and 9% there is overshoot, time constant, and settling time is 1.66. Also, you can find out the specification using inbuilt function. So there's something called stepinfo function, and you can run this. So you can see that the can you see the overshoot is 9.48, and it is matching with formula with inbuilt function. But last time it is not matching, it's 0.692 and 0.46. Why it is like that? Let me show you here. By default, it is taking the rise time between 10 to 90%. But in the case of overdam, it is between 0 to 100%. So how you can change it? If you read this detailed documentation, you can find the details. Let me find out. Just 1 minute. So you have to limit the rise time. You want to find out between 0 to 100%. So that you have to write. I think okay, it should be here. Yes, the rise time limit. So I have to change the code. Rise time limit. I have to write in code, and between, see, by default it's showing from 0.1 to 0.9, so I will change from 0 to 100%. Now if I run this code, you will see the rise time is 0.69, which is matching with what we have calculated from formula, right? So that we have verified. Now this is also very important, the relation between zeta and MP. So what I've done, I've taken value of 0 to 1, and there is a maximum overshoot formula. So I've plotted zeta versus MP. Let us run and understand. So when zeta is equal to 0, there is 100% overshoot. Uh, I have not take I have taken between 0 to 1, but let me do here just multiplication of 100, so I can get between the scale is 0 to 100. So when I take zeta is equal to 0, there is 100% overshoot. As I increase the value of zeta between 0 to 1, the overshoot is decreasing for the second order system, right? So